So the simulation software we use for this is Simulink, which is built in MATLAB. With the help of Simulink, we can build different models with the help of blocks and simulate with graphical modeling. So let us see the block first. So what is QPSK? QPSK is a QPSK is a multi-level modulation in which 4 phase shifts are used for representing 4 different symbols. So the blocks used are like random integer, which is used to generate random integer bits or binary values. Then we have used QPSK modulator and demodulator. So the modulation and demodulation demodulates the signal and demodulates the signal at the output. Next is a AWG channel, which is a wide Gaussian noise. So after the signal is modulated, the noise gets added to our channel. As we see in our QPSK modulator output, the output gives a complex signal, which needs to be simplified. So we use different blocks, which are like real, imaginary, and sine and cosine waves, which will simplify our waveform into sine, cosine waveform. Next, we see the constellation diagram block, which will show us the graphical representation of a signal with noise added in it. Next is a error rate calculation. Error rate calculation is something which is used to compare the input data from a transmitter with an input data from a receiver, and it will calculate the error rate. So let us see the working of our simulation. So first, this is a random integer block. So we have used 4 M-array numbers. So in QPSK, there are 4 phase shifts. Next, which is a QPSK modulator baseband. And we have used a gray as a thing, and input type is an integer. So let's see how the blocks work. So first the input we have taken as an integer, then it goes to a modulator. So the signal gets modulated. As we know in QPSK, the signal is in a complex form. So we need to simplify it. So we split the signal into real and imaginary parts. So the real goes with a sine wave and imaginary goes with a cosine wave. So it gets multiplied with the real with sine and cosine with imaginary with cosine, and we add it, and the simplified representation will be seen in this scope screen. After this, we see in this, after the modulated signal comes out, it goes into an AWG channel where the noise gets added. So we can see in a constellation diagram. So let's see it. So this is a constellation diagram. In this constellation diagram, there are 4 phases, which is pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi by 4. It will vary accordingly for different modulations. So as we can see, this blue dot represents the noise, and this is a phase shift. So difference between this point and this blue dot is due to the noise which is added in the AWG channel. So this noise causes the points to spread out. So for this constellation diagram, the main thing we need to focus is this point should be focused near to the signal. So the more the points are focused, the better the noise will be.
From this, we conclude that when the SNR ratio is high, then the quality of the signal is high because the dots are more concentrated near the 4 points. The next output waveform which we are going to see is the one that we obtain at the add end. Now we know that the modulator output is in the complex form. But in order to study the phase shift and in exactly how phase changes, we need a simple sinusoidal wave. For that, we split the complex into real and imaginary part, and the real and imaginary part are respectively multiplied with sine and cosine waves. and then they are added in order to generate the modulated tone. So this is the modulated waveform, and this is the input generated by the random integer generator. Now, the random integer generator generates a different waveform at every simulation. In this particular simulation, we are getting this waveform. Now, in BPSK, we know that there are 1 bit transmission per symbol. But in QPSK, there is 2 bit transmission per symbol. So in BPSK, there is a 180-degree phase shift, whereas in QPSK, there is 90-degree phase shift for 0, 1, 2, 3 are nothing but the levels which resemble or represent the symbols. That is 0 represents 0, 0, 1 represents 0, 1, 2 represents 1, 0, and 3 represents 1, 1. Now here we see that at the very start, the level is 2. Then it changes to level 0. So we can see here that 2 to 1 represents 90 degree and 1 to 0 represents another 90 degree. So 90 degree plus 90 degree gives us 180 degree. So here we get a continuous waveform and there is no 90 degree phase shift in it. Here the 0 continues till 0.3. So the waveforms still continues till 0.3. And as we can see, there is a change in 0.3 as 0 changes to level 1. So there is a 90 degree phase shift. So in 90 degree phase shift, basically what happens is that the waveform is inversed. So this continues till 0.4 when there is again a level shift from 1 to 2. And thus the waveform is generated when there is a shift of 90 degree, then there is a reverse in the waveform. When there is 180 degree shift, then there is a continuous waveform. So the next waveform which we are going to observe is the demodulator end waveform. So here, this is the input waveform and this is the demodulator output waveform. So these two waveforms are replica of each other. That is, both the waveforms are exactly similar to each other. So from this, we can conclude that there are no bit errors generated in this simulation. And the correct information is received at the receiver end. So the next important point is the error rate calculation. The bit error rate calculation helps us to denote how much error is generated in the transmission and how many bits of error we are getting. So the display box contains 3 quantities. First is the BER rate. Second one is the total number of error bits generated. And the third one is the total number of bits. So the formula for bit error rate is bit errors upon total number of bits. So 0 by 11 gives you 0. So this can be cross-verified as at the demodulator end, the waveform was exact replica of the input. Wherein we have changed our SNR value to 0. That is, we have reduced the SNR value. So this transmission is prone to more noise and errors might be generated during this simulation. So after simulation, we got an output wherein we received a BER rate, that is bit error rate of 0.09, which tells us that some error is introduced during the simulation. So here we observe that a total number of error bits generated during this transmission is 1 and the total number of bits transmitted is 11. So BER rate according to the formula will be 1 by 11, which is 0.09. So some errors might be introduced in the demodulated waveform. That is, there might be some changes in the demodulated waveform. Modulated waveform. So when we compare both the waveform, that is the input and the output waveform, we can see and change in the second bit. So during transmission, the bit was supposed to be 0, but at the receiving it, we have received bit 1. So this is the one error bit that has been generated. And when we see the rest of the waveform, it is same as the input. So we can cross-verify from the waveform that total one error bit has been generated in the entire transmission. So when the SNR ratio is 0, then the signal quality is reduced and it is more prone to noise and errors can be generated.